Hello and welcome back to question 10, differential equations. Now, you might notice something different today. I'm sitting down. There's no pre-written solutions. Why is that so? Because I think for questions like differential equations, it is actually important to look at the thought process of doing the working itself, right? So the devil is in the details. So then the trade-off, of course, is you have to suffer and watch me write throughout this video, right? Feel free to, speed up the video if it gets unbearable. Now, let's talk a bit about differential equation first, right? Why are you even learning this? What does it actually do? So sometimes, say if I'm interested in modeling things in real life, for example, the population of rabbits, right? Given that the population of rabbits doubles every 4 days, I could use something very simple, for example, 2a, where a is some constant, divided by 4t. T is the number of days, right? So that can sort of tell me what is the population of rabbits at a certain day. That is fine and good until you realize that, hey, what if I want to model like the second day or the third day or even 2.3896 days, right? When we no longer count time in discrete steps, when we count it continuously, right? You know time is continuous, right? So when you want to do that, you realize that this type of modeling breaks down very quickly. And what you have to resort to is actually differential equations. Because at the heart of calculus, what we are doing is we are calculating small continuous change. And that is why I will say that 99% of the time, if you're trying to model something in real life, something that's continuous and always changing, you will have to resort to differential equations. So this is the one topic, if you ask your teacher, where am I going to use this? Your teacher will roll their eyes and like, all of the time, okay? Assuming that you're still going to be in the fields of mathematics and science when you graduate. So let's take a look at this equation. What is this dE? Right, this is what we call dE, trying to show or trying to tell us. Right, this is something that is supposed to model the growth of cancer, lung cancer, right, or specifically the volume of a tumor. Okay, so V is the volume of the tumor. T is time in days, right? Although that it seems like time is in discrete steps, but again, we could do like 1.328 days, it's still considered continuous. Okay, so dV dt is the rate of change of the volume of the tumor, right? How much your tumor is growing or shrinking, right? It's modeled by this equation over here. Some constant A times the volume times natural log of K over volume. Okay, where A and K are positive real constants. Now let's look at part 1. Part 1 is a straightforward 1-mark question. It says, what happens to dV dt as V approaches K? So let's look at this equation. Maybe something that links V and K will be the argument of the natural log function. Okay, as V approaches K, then this fraction becomes more and more like K over K, which is 1. So natural log of 1 is 0, and that tells me that dV dt will be 0, right? dV dt will be 0. Okay, then that's all you need to answer. You don't even need to answer in context of the question. But if you're interested in context, it tells me that as V approaches K, then the tumor will neither shrink or grow, right? It means that it will start to be, it will not change as it approaches K, right? So that is part 1. Now in part 2, we have to use a substitution to solve this dE. What does it mean to solve a dE? To solve a dE means to give me the equation of V. Because what you have here is V, how V changes with time. But what if I want to know what is the volume at a certain period of time? Then I need to know what is V of t, right? V as a function of time. And you find that, wow, this is really hard to integrate. In fact, if you're going to stay in maths and science and do differential equations in your job next time, you find that a large percentage of differential equations cannot be solved. Okay, so you have to be creative about it and do a substitution. Okay, so in the syllabus of H2, you will always be given the substitution, or you'll be given a dE that is directly solvable. So this process of coming out with the substitution is something that takes days, weeks, months, right? It's not something you can do in 20 minutes or an hour. So definitely don't worry about it. Okay, and after solving it, can you show that V is equal to this? Where capital A is some arbitrary constant, i.e. is something that you get from integration, your constant of integration, right? So let's do this. If I want to do a substitution, meaning that maybe I don't want to write it as dv dt, I want it to be du dt, and every instance of v, I want to replace it with a u. Okay, so first things first, maybe I want to look to write down v in terms of u. Then I can substitute away this v. Right, for this one, no problem, because sorry, let me just very quickly circle this. This one is actually going to be substituted with this one. Okay, so no problem with that. I just need to write down wrong color, v in terms of u. Okay, so this is the question again. dv dt is this, and this is my substitution. So maybe let's make v the subject of the formula. Right, to make v the subject of the formula, I need to take e to the power u equals to k over v. Okay, making v the subject of the formula, I get k over e to the u. Next, if I want to change this thing, I need to change this to du dt also. Du dt will be dv dt times du dv. So I need du dv. Right, I have to differentiate this with respect to v. Okay, that gives me differentiating this natural log function. Differentiating natural log, I get 1 over the argument, which is v over k. Then I have to differentiate the argument itself. That is a negative k over v squared. Okay, that gives me a negative 1 over v. Okay, and now I'm ready to do my substitution. Du dt is equals to dv dt times du dv. Right, this is by chain rule. Right, you can sort of think of like the dv and the dv cancel out, but don't actually go and cancel it out. Okay, so dv dt is going to be this one, a times v times u. A times v times u. Okay, times du dv, which is negative 1 over v, which nicely cancels out with this v over here. So actually I didn't even need to use this one, this substitution. So that is a negative au. This is equals to du dt. Then I can do, this. I can say the integral of 1 over u du is equals to negative a integral of dt. Okay, so differentiate, integrating both sides, I get natural log modulus u equals to negative at plus my constant of integration. Okay, then to make u the subject of the formula, I'm going to take this e to the power of negative at plus c, which can be written as e to the negative at times e to the c. Right, now next thing is this is a bit hairy, right? Because modulus u tells me that it could be positive u, it could be negative u. So let's go back to the context of the question and see if I can, reject one of them. Right? What is u? U is given to be the substitution natural log of k over v. Right? Could this be negative? And the answer is yes. Natural log can return a negative value when you have a value that's less than 1 inside here. If it's less than 1, it means that v is bigger than k. Are we given anything from the question in context where v could be bigger than k or smaller than k? Turns out the answer is no. I have no way of telling whether u is going to be positive or negative. So then this is what I generally don't really like. So I'm going to write u as plus minus of the right hand side. But I'm going to reorder this. I'm going to write the e to the power c in front, and you'll see why. That's e to the negative at. Okay, we can absorb this. This is quite a good technique actually. We can absorb it as just some constant. Right. We can say that where a is equals to plus minus e to the c. Okay, and this is u. So you might think that we have solved the dE, but we actually solved the dE in terms of u. We want to solve it in terms of v. So let's put u equals to, let's substitute back our natural log k over v as u. Okay, and then to remove the natural log, I have to raise e to the power of a e negative at. Okay, making v the subject of the formula, that will be k times e to the negative right? Because it's 1 over. And there, we have managed to show what we are supposed to show in part 2, right? Great. Now let's look at part 3. Part 3 says what happens to V? What happens to V as t approaches infinity? As t over here gets larger and larger. Okay, as t gets larger and larger, maybe let's look at, let me use a different color, huh? Maybe let's look at this first. What happens to this term over here? A e to the power negative at as t approaches infinity, yeah? As t gets larger and larger, right? Then I can say that this thing is going to approach. So this actually is your negative exponential graph, because I know a is positive constant, huh? So this is a graph of decay. Remember your exponential graph of decay? It means that as time approaches infinity, then this thing is going to approach 0, right? So the whole thing will approach 0. I can say that this is going to happen. Okay, if that is going to be 0, then I can say that k e to the negative a e negative at is going to approach. Okay, so this is 0. This whole thing will just be e to the power 0, which is 1, and therefore it will approach k, right? So I can say that v is going to approach k, because this is actually equals to v, right? This is actually equals to v. So as time approaches infinity, the volume will approach k. So what does that mean? If you give enough time, right, as days pass, the volume of the tumor will approach this value k. So that tells me that k is sort of like the limit of the volume of the tumor, or the maximum volume of the tumor. Okay, this is part of the question. You have to give in context what's the meaning of the significance of k. K is the maximum volume of tumor. All right, now let's look at part 4. Part 4 is where we finally get some real values, concrete values for a, k, right? So we're given that, let me just underline the question for part 4, part 5. A is equal to this, k is equal to this, and we know that v is equal to this when it was discovered early. What does it mean to discover early? Then you go back to the question, huh? Okay, so an early discovery will mean that your t is equal to 0, right? T is measured in days after an early discovery. So at the point of early discovery, t is actually equal to 0 days. Yeah? So I know that this one, and t equals to 0. Or rather, I should say that v equals to 100 when t is equal to 0. Okay, and I can substitute all these things in, because then you see I only have one unknown. This is 100, this is 8,000, this is 0.01, this is 0, right? Then the only unknown that I have is capital A. I can solve for capital A. Huh? So let's do this. This will be equals to 100 equals to 8,000 times e to the negative a e to the power 0. Okay, e to the power 0 is 1, so that's 8,000 e to the negative a. Okay, so what I'm going to do is I'm going to write this as e to the negative a equals to 1 over 80. Okay, skipping a few steps here and there, right? So just take a while to digest that. Okay, next I'm going to take a natural log on both sides. So this is going to be negative a equals to natural log 1 over 80. A is going to be negative natural log 1 over 80, which actually is the same as natural log of 80 over 1. Yeah, so a is equals to natural log of 80. And that makes sense, because remember back in the steps where we had to write a as a plus minus value, now we know it's a positive value, right? Why is that so? Because if you go back to our consideration of this, do I know what is the value of this fraction? Is it always less than 1 or more than 1? Aha, now I know it's more than 1, because k is the maximum value and v is something that's always smaller, right? So in that case, this will always be more than 1. My u will always be a positive value. Therefore, my a would be a positive value. Right? Natural log 80 is a positive value. Huh? Okay. So there you go. But this is not part 4, because part 4 you're actually supposed to find the size of the tumor at 100 days after early discovery. So let's sub t equals to 100. Okay, so when you sub t equals to 100, let me just very quickly look at my answer that I worked out previously, because here you have to press calculator. V equals to 8,000 e to the negative natural log AT, right, times e to the negative 0.01 times 100, which is just negative 1. Okay, so if you press this out, you get 1595.81413, which you have to round to the nearest cube, right? So cube, let's check. This question is V. Right? V is given in cube. Sorry, let me change color. V is given in cube, right? So no need to change anything. My answer will be 1596 cube. That's the answer for part 4. Now for part 5, you have to sketch the graph of V against T. Right? Again, let's write down the equation. V equals to 8,000. Right? Let me just take a look. E to the negative natural log AT. E negative 0.01 T. Okay, so this is part 5. Let's sketch this graph. So let's use the GC. Let's use the graphic calculator. And why is it not showing? Strange. Aha, there you go. Right? So this is what you have to put into your GC. Should I make this bigger? Let's see, do I get to resize this? Yeah, I do. Sorry about that. Now let's make that much bigger so we can all see clearly. Okay, now let's graph this. Okay, when you click graph, you might be surprised that, wow, is it taking so long to plot? Actually, no. You have to actually look at, say, this part here. If there's a spinning circle, it means that it's drawing. This means that it has finished plotting out or graphing the graph. If you see something empty, do not worry, because, okay, let's go back. Let me remove the calculator first. Why are you not seeing anything? That is because, if you remember, right, one of the things we know, when t equals to 0, v equals to 100. So that means maybe my scale is not there, you know. And when t approaches infinity, I'm looking at v equals to 8,000. Right, v approaches k, remember, this is our k. Okay, so I want my graph, my y-axis to be between, say, negative from 0 to maybe 8,200 to see the whole height of the graph. Okay, and since I'm going towards infinity, maybe I need a larger t value. Maybe we can experiment a little bit. So let's go back to the GC. Let's go to the window, right? Instead of doing zoom standard or zoom square or zoom out, go to window, right? And then we need to adjust these values. Okay, x minimum is negative 10. Maybe I want this to be a bit larger, maybe 1,000. Okay, x scale, maybe let's do 100. You know, minimum y, maybe I can put it at 0. Maximum y, I'm expecting to be 8,000, right? K equals 8,000, maybe 8,001. Then the y scale, maybe 100 or so. Oh, actually no, I need to show 8,000, so maybe a bit larger, 500. Okay, so when you graph it out, now you get to see the curve. It looks like this, like an S shape, right? You might know this as the sigmoid curve or the logistic curve. It's the curve that actually models COVID-19 cases as well. Okay, so then we can sketch this out, right? Roughly, we know that there are two asymptotes. One asymptote actually, one at the top. The bottom one is not asymptote. It cuts the your vertical axis at 100. Okay, so let's plot this out. Oops, I ran out of space. That's the next question. So just to keep it small, do something like this. Okay, the actual shape doesn't really matter, but you need to make sure that it's sort of like an S. Okay, and then you can do a straight line here, dotted. Say this is V equals to 8,000. This is 100. This is V. This is T. Okay, don't forget to label your graph. V equals to 8,000 e to the natural log AT minus e to the negative 0.01 t. Right, and that is part 5. And we've completed question 10. I hope this was helpful, going through the entire question like that. And yeah, leave a comment, tell me how you found it. If you prefer the previous way, let me know. Until then, I guess I'll catch you in the next one, question 11 on vectors.